Hello and welcome to a new episode of What's New in SimCenter AMISIM 2511. In this video we'll explore the latest platform and library new features, along with updates on connectivity, documentation and so much more.
Yes, and we will do that by demonstrating the workflow for creating a fuel cell electric vehicle model, illustrating how most of these videos work in practice. Remember, these capabilities are applicable to your industry as well, whether it is aerospace, energy or marine.
Today we'll go through 30 of them, all organized into 7 distinct sections. Feel free to pause the video now to review the full agenda.
And as always, you can navigate using the timecodes in the video description. So without further ado, let's get started. Our mission is to develop a fuel cell electric vehicle that meets performances, safety and integration requirements. We will need multi-domain modeling, productivity and collaborative tools to succeed.
We'll start with the vehicle chassis model, then dive into the fuel cell and battery models, then electrical motors, thermal management system, and finally the overall vehicle integration. So let's finally start SimCenter AMISIM 2511. But before we do that, we need to access the license. In SimCenter AMISIM 2511, we've introduced the SimCenter X Advanced Cloud Licensing feature. This is a completely new approach to license management. Licenses can be stored in the cloud, reducing deployment time and simplifying licensing process. This can be used not only for SimCenter AMISIM, but for other SimCenter software as well, unifying and simplifying licensing workflow.
Indeed, and you'll notice that SimCenter Client for Git is in the list. We can just mention that our collaborative data management solution now features the possibility to store large files, so-called LFS, which allows to download and upload repositories much faster. It's also now possible to delete branches, which enables you to keep server collections small. Now, let's start SimCenter AMSIM.
Before we start building the model, this release introduces an integrated AI-enabled chat inside SimCenter AMISIM for all cloud license users. It has access to all documentation and can quickly answer your questions based on that. Plus, we keep improving it in the future, so definitely start using it today.
As always, if you need more information, you can find it in the SimCenter AMSIM help, which has also been updated. It's now available on your web browser and includes an improved search workflow, clean PDF export, and multi-language support. That means you can translate the content of the help page into your preferred language with just a click of a button. Now let's start the modeling of our fuel cell vehicle. We begin with the chassis, and since I'm always looking to optimize my time, I'll start with an existing demo. There is a new demo including a 3D chassis components, templates, and its comparison to our 15 degrees of freedom chassis model. In this demo, we compare both modeling approaches.
It's worth mentioning that we updated the 15 degrees of freedom model to have clearer model variables and folders, making it easier to retrieve results thanks to the new structure with axle and wheel folders.
This demo shows how the 3D chassis components compare to the 15 DOF model, yet allowing more flexible chassis configurations such as 4-wheel steering or to directly import the hardpoint positions from a CAD. As an example, we can see here that the toe, the camber and the self-rotation angles match perfectly between the two modeling approaches.
As I can see, this model doesn't have any wheels included.
No, you're right. So let's open another new 2511 demo that includes wheels, track and a driver. This demo can be found in the chassis sections of the help page and shows detailed 3D vehicle model driven on a looped circuit.
Working with several models and comparing them can be a difficult task. Understanding the difference not only in results, but in parameters and components used can be hard, but we have a tool for that as well.
Yeah, this is something we can check with the updated model comparison tool. The tool has been improved to be able to visualize both sketches and to compare easily the different parameters, including inside the super components and the global parameters.
Now that we confirmed those are the same chassis models, we can go ahead and focus on tire components.
Well, this tire component model features MF Swift or CD tire models that now can be parallelized for faster computation time. We can add that this whole chassis model is real-time capable and can be executed in driving simulators or hill test benches. To help you with that, there is another new demo which demonstrates how to export such a model on concurrent real-time platform, for example.
Now we have our tires all set, we can choose a test ground or a track profile.
Yes, and let's open the trajectory import tool that can be launched from the driver controller app. So here it's an oval track, and here I want to highlight the fact that in SimCenter AmSim 2511 we can now loop tracks, so that we can go round and round for a while with this model.
And it's also worth mentioning that in these tracks you can edit the ground to add obstacles such as bumps or holes, and now batch run them using the Study Manager, meaning you can add dimensions of those road imperfections into the Study Manager and use batch run just like you do with any other SimCenter AmSim parameter.
Yes, indeed. So let's now move on to the powertrain. We will start from the fuel cell integration demo that was released in 2504 and that leverages the new gas library. This demo illustrates how to model a complete fuel cell system, including the stack, the balance of plant components, and the control systems.
There are some important updates in the gas library too. It now features the new Redlich-Kwon equation of state, which gives the user more choice when selecting the most appropriate equation of state. New flow characterization method based on the ISO standard. That means you can provide a direct set of parameters from the ISO datasheet directly. You don't need to convert them to CQs or KVs anymore. The fuel cell stack model also includes updates on the polarization curve identification tool to compute the Nernst potential using the Gibbs free energy of the reaction and with the temperature and partial pressure dependence, making the parameterization of the fuel cell submodels simpler for the user.
These are nice improvements to the existing solution indeed, making model setup faster and easier. But my personal highlight for the 2511 is the new fuel cell aging model and its associated identification tool. We now can take advantage of this model to refine the design of the fuel cell system and its control, considering the degradation of the stack performance from its beginning of life up to its end of life. See how the tool works.
The user basically inputs different polarization curves at different lifetime of the stack and first identifies the corresponding stack electrochemical model parameters, just as previously showed in the app.
Then the tool will identify corresponding aging laws for the current densities, membrane conductivity, and concentration voltage coefficient. These will in turn allow the model to compute fuel cell voltage drop due to aging. These are comparisons of experimental and simulated data for different aging times. Finally, the aging model is sent into SimCenter AmSim's fuel cell submodel.
And as usual, it's not only a matter of providing the equations, but also to provide a tool to simply feed these equations. On a side note, our tank models have been increasingly utilized. So let's highlight some of the improvements made in the latest SimCenter AmSim 2511. From this release, we can define two-phase flow mixtures. To do that, select the fluids that will be added to the mixture from our fluid database. That means that our tanks support two-phase flow mixtures too, allowing you to simulate more complex scenarios of multiple fluids mixed, one of which can condensate. We also improved tank parameter definition, where now you can define liquid mass directly instead of recalculating it manually.
On the battery side, we updated the recently released Battery Pack Assistant with the capability to import cell electrical data either from our database or from an existing model. Let's open the app from the App Space to discover this.
AppSpace is the place where you can now find table editor, CAD import, as well as many other useful apps for pre- and post-processing.
Indeed. So let's look at the Battery Pack Assistant. When you open it, you see two new buttons, Get from Database or Get from Models. These two new options will allow you to speed up battery pack design and minimize parameterization error by getting the correct electric model into the battery pack. We will select the current battery pack electric model of the sketch, and then we configure the pack assembly and thermal management. Here is another new feature, the capability to discretize the thermal model of the pack in any direction to better capture thermal gradients. especially useful for large cells like the one from BYD Blade.
Once the pack is generated, we can replace our former battery pack with the new one, which includes the cooling plate. When running a simulation, we have access to the maximum, minimum and average battery pack temperature, as well as the maximum temperature gradient between the hottest and the coolest cell. All predefined variables from the generated supercomponent.
That's very useful when you design the battery management system, estimate the fast charging capability, or analyze requirements for the thermal management system.
Yep, that's it. Let's now switch to the electric motor model of our powertrain.
Yes, and we have important updates in the induction machine model. In this release, we updated our squirrel cage induction machine and added detailed losses and nonlinear inductances simulation capabilities. This new model will allow us to capture the impact of temperature-dependent losses on e-powertrains and improve the efficiency predictions with comprehensive modeling of DC, AC, and iron losses. Here, we will copy this model and its corresponding thermal management and control system models into our fuel cell and to replace the current functional model of the permanent magnet machine.
We run validation simulation to check if electric machine model runs well within powertrain, and we can plot individual temperatures of the induction motor parts. We can now accurately estimate the heat released by the powertrain's components. We can start resizing the thermal management system.
Imagine you have design engineers who already worked on the piping network and released a piping and instrumentation diagram, or so-called P&ID. In SimCenter AMSIM 2511, we can now automatically generate the P&ID corresponding model as shown here. This enables us to rapidly generate complex 2D piping networks definitions without any loss of information. Here is an example and the comparison of the model generated with the original P&ID diagram. We will then connect the piping network to the existing thermal management system.
And for the heat exchanger?
We can replace the dummy heat exchanger with a new functional half heat exchanger model on which we can specify the outlet temperature target. This is useful to quickly calculate the heat flow rate needed to meet the design requirements. In this example, we set an output coolant temperature target of 35 degrees C and run a simulation.
Okay, here we see that we need a rather large heat exchanger to keep the outlet coolant temperature at 35 degrees. Let's use the heat exchanger assistant to generate the heat exchanger we need.
Yes, and here are several new features to help sizing the best heat exchanger. If we don't have any geometry available but still want to easily transform performance requirements into a ready-to-use model, we can use the new geometry-free number of transfer unit (NTU) modeling with parameter identification. Here we'll need experimental data of the heat exchanger performances to be able to optimize the NTU model parameters. After optimization is complete, we can generate the corresponding model.
If we want to model a fin and tubes heat exchanger and have the geometrical details, we can leverage the discretized modeling approach directly from the heat exchanger assistant. This approach enables built-in heat exchanger intuitively using an integrated 2D and 3D visualization.
Okay, and what if I would preferably go for a multi-core microchannel heat exchanger?
Then the same approach has been added to this kind of heat exchangers as well. Here you see that we can now define the number of cores and configure them independently.
And I can see that the heat exchanger assistant now summarizes mass and dimensional data during the geometry definition phase. This will be helpful to verify the heat exchanger design against system requirements early in the development process.
See how it automatically generates the complete model with fully parameterized components. With the new heat exchanger, we have a ready-to-pack powertrain. We can integrate the powertrain into the vehicle. We'll run a new simulation to make sure that the heat exchanger performs well and that powertrain temperatures are kept under control and matching the requirements.
Did you know that the step of assembling the powertrain and the chassis during the manufacturing was called the wedding?
The wedding? Oh, that's sweet.
So let's proceed to the wedding of our powertrain and vehicle models. With such a model, we can verify the thermal safety and durability of the powertrain components, the vehicle dynamics performances, the energy consumption, and even get into NVH characteristics of the e-machine and the inverter. That looks like a great integration platform, right?
As an example, we perform a design of experiment varying the gear ratio and the regenerative braking strategy. We'll look at their impact on the maximum pitch angle of the vehicle, as well as the hydrogen fuel consumption using the new data relationship plot capability. This allows to quickly understand parameters' influence and get insights into local sensitivity. Here we look at the impact of reduction gear ratio and regenerative braking strategy on the maximum pitch angle of the vehicle.
And that were the last features we will cover today. Check out our release blog to get more information about some of these features presented today.
I should add that there are many more features to discover. The full list is, as always, available in the release notes of SimCenter AmBSim 2511. If you haven't downloaded it yet, you can do so through our support center. The link will be in the description of this video. This is also the place where you can open support cases, read knowledge base articles, watch video workshops, and so much more.
And if you're completely new to SimCenter AmBSim, you can anyway request for a free trial and gain instant access to our cloud-based SimCenter AmBSim installation. Combine it with 15 videos from our Getting Started series available on YouTube, and you're good to go. All links are available in the video description.
Thanks for watching and see you in the next one.
Bye-bye.